Okay, good afternoon, everyone. Let's hope the system and the computer behave itself. So as I was just mentioning a little while ago, in the morning's class, computer was fine, but the projection system was messed up. And so we couldn't see anything from the screen over there. But we restarted everything and hopefully it should stay, well, it should stay in working condition. Okay, so rectifier circuits, let's see. Change. Okay. And recording is on. All right, so we looked at the basic half-wave rectifier circuit, right? Which is comprised, yes. Oh, rectifying is basically converting from AC to DC. So a device that converts AC input to DC output, we call it as a rectifier. Anything that converts DC to AC is called an inverter. It's called an inverter. It inverts, so it's inverter. You can actually buy commercial inverters for your car vehicles. So you take a, you can buy an inverter which has an AC outlet that plugs into your car's 12-volt or cigarette lighter outlets, and you can have 120 volts AC running in your vehicle, car vehicle. It's about 15, 20 bucks. It's not that expensive. Anyway, so rectifier circuits. We looked at rectifier circuits based on diodes. Diode has the property of one-way operation, kind of like a one-way street. And so the rectifier circuits are based on diode circuits. So half-wave rectifier we looked at had a single diode, right? A single diode, and then we saw how the operation of the circuit. We saw the operation of the circuit where the diode works in 1/2 cycle, so it conducts current in 1/2 cycle, then it's off in the other half cycle, right? Now the obvious disadvantage here was there's a missing piece right here, right? Because it's empty. There's no output during that time frame. There's no output during that time frame. Now the AC that comes from the power outlets is 60 hertz. So there are 60 cycles in 1 second, right? 60 complete cycles. So you would see 60 of these peaks in 1 second. So the average value of the waveform would translate to a DC level voltage. It translates to a DC level voltage. Yeah, it's not the board. It's not. Yes, I'm recording. And that average voltage is around, well, for a full wave, it's around 0.367. But for a half wave rectifier, the average voltage is around 0.318. So the average value of that voltage waveform for a half wave rectifier is 0.318 volts of the peak or the VM value. Okay, peak or the VM value. So if the peak value of the waveform is 10 volts, then the average DC value at the output of a half wave rectifier would be 3.18 volts. Yep. So average DC value for a half wave rectifier, if VM was 10 volts, VDC would be 3.18. So just think about it. If you want a 3 volts DC outlet from a half wave rectifier, you would need a transformer that is capable of giving you at least 10 volts, if not more. And this is for an ideal diode, right? For a real life diode, you'd still have to subtract 0.7 volts from this output in order for it to turn on. So it would be VM minus 0.7. Okay, this is for ideal diode. This is for ideal diode. That is what we see in these waveforms. right? The difference, this is basically the threshold voltage that is required to turn on. So diode turn on voltage. Make sense, right? So obviously this is not a very efficient, circuit, right? And so we have something known as full wave rectifiers. So half wave rectifiers, again, as I said, early on, really cheap adapters were the ones that actually used these. So here I brought a few things for like show and tell. These were known as wall warts. Even the smartphone chargers that we get nowadays are wall warts. This is simply a transformer. So typically we used to have these kind of devices, adapters, that would have a transformer and would have diodes and capacitors and resistors all inside one box. But this is specifically a transformer. It is actually a step down transformer. So you plug it into the wall and it takes the 120 volts AC that's coming out of the power outlet and steps it down to 12 volts AC. So the output over here is 12 volts AC. It's not rectified. I just wanted to bring it in, just show, a little bit of show and tell. And then I'm assuming most of you are taking the lab, right? So you've already worked with the diodes, but in case you haven't, these are the diodes that that are the most common ones in common usage. So I've seen adapters where they would simply take the transformer out and they would, without a circuit board, they would just take like diodes and twist the leads together and build a circuit like in the air, kind of. You just take the leads, you twist the turns, attach a capacitor, and you have a rectifier circuit. And well, those are the cheap ones. Real nice ones, they actually have a circuit board. Okay, so moving on, full wave rectifier, right? Full wave rectifier. Oh, with regards to the transformer, so the point I wanted to make was here you in the circuit diagram, you see it's Vs of t, right? It's a generic symbol for like some sort of AC voltage, right? So if I wanted to actually draw a circuit diagram with a transformer, this is how it would look. This is the symbol for a transformer. This will be the diode, and this resistor would be your load. So transformer, 120 volts AC coming into the transformer, stepping down to, let's say, 12 volts, 120 volts input, stepping down to perhaps 12 volts. And then, of course, going through the diode, and we'd get rectified waveform, right? Rectified waveform. Now, continuing on with the point I was making earlier, that half wave rectifier is not very efficient. We lose half the half the capability because the negative half cycle is not being rectified. And so they came up with full wave rectifier. Now this is a specific case of a full wave rectifier. Early on, now here you can see there are two voltage sources, right? So early on when they were working with transformers, they would have something known as a center tap transformer. So you have your input coming here. And you have a center tap transformer. That's how it would look. When it shows you like dual power supply in here, well, in real life, it's not going to be like that. You're not going to have two actual separate power supplies coming in. It's basically one unit, like the transformer that I'm sending out. It's a transformer, but somewhere in the secondary coil, there's a wire that's coming out, and we call it a center tap transformer, center tapped. So this circuit is known as a center tapped full wave rectifier. Okay, it's a center tapped full wave rectifier. Just in terms of illustration, it requires two sources. And the reason it requires two sources is because in the positive half cycle, diode A would be on, and in the negative half cycle, diode B would be on. Now, the reason it would do that is because when you talk about AC, the positive and the negative polarity would interchange, right? Electrons go forward in one direction, in the negative half cycle, they're going back. And so the polarity would change. So let me take this circuit and illustrate how it would work. So in the positive half cycle, you would have something like this. Center tap, so positive half cycle, the polarity of the voltage would be like this. So what happens? Diode A is on. Diode B here has the negative voltage connected to the diode to the anode, and so B is off. So this in the positive cycle. Right, diode A is on. So the current actually goes from this A, this diode, and goes through that load resistor from the right to the left. Okay, thus completing your circuit. It goes from right to the left. By the way, this load connection is the exact same as this one in the diagram. Obviously, when you show ground here, it shows you that the resistor is connected right there. Okay. All right, in the negative half cycle, the exact opposite happens. Voltage reverses polarity. And so now you have minus, you have plus, you have minus, you have plus. And so diode A turns off and diode B turns on. So now again, the current is actually flowing in the same direction. Going from right to left. So for the load, there is no difference. In the positive half cycle, current's going in one direction. In the negative half cycle, also the current's again going in the same direction. And so you get this kind of output right here. Each diode handles the one half cycle each. So diode A rectifies positive cycle, diode B rectifies the negative cycle. Does that make sense to everyone? All right, questions? Any questions? Yes. Yes. So positive cycle, A is on, current's going through the resistor from right to left. And the same thing here. Yeah. And then diode B is the exact same thing. Diode B turns on in the negative half cycle. Current again goes to the load resistor from right to left. And so the load resistor waveform is shown in this characteristic right there. Yes. So it shows two sources just to show, well, it is just a general source. But in real life, as I was saying, it's an actual transformer. It's a single transformer. And the transformer just has, like, in the secondary coil, there is a tap in the center. So you're tapping into that source, and so it comes out. And when you do that kind of tapping in there, the transformer behaves like two different outputs. So in real life, that's what it is. But nowadays, since transformers are, these kind of transformers are no longer used, And so most people are not familiar with what a center tap transformer is. If you were to talk about center tap transformer, chances are even an EE student probably doesn't know what it is. Yeah, it's quite possible. We don't use them anymore. Well, at least for the most part, we don't. Nowadays, everything is solid state. Well, not even nowadays, even going back like 20, 30, 40 years, everything is now solid state. So as a real life example, in many parts of the world, instead of using like air conditioning, you just use fans, right? Here in San Luis Obispo, Santa Barbara, the weather is mild, and so there is no air conditioning anywhere, right? So many of the houses, many of the places, and similar to many parts of the world, there are like ceiling fans. So the ceiling fans now have regulators. You can increase or decrease the speed, right? Anyone know what I'm talking about? Right? So even before that, solid state versions of those dials where you could decrease the speed, older mechanisms actually had just a transformer. And it would be a huge box that would sit on the wall, and it would have like five or six settings. And there'd be a dial, you would just click and change. And what was happening every time was when you change the position of the dial, you're tapping into a transformer that has like 5 or 6 different outputs. And so depending on where the output was, the voltage that is coming out of the transformer is different. So you could have like 25 volts and 50 volts and 60 volts, 100 volts coming out from the transformer at different spots. So you change the dial, you're changing the voltage coming from the transformer, and thus you're changing the voltage being applied to that fan. Thus you're changing the speed of the motor and the wind that's coming down on you. So again, as I said, everything's gone to solid state, so we don't use those kind of transformers anymore. If I find a device somewhere, I'll bring it in for show and tell. But I don't think I'll find something like that in the US. I'd have to go, I don't know, junkyard shopping. Anyway, does that make sense? Full wave rectifier. So even this is not very widely used anymore, center tap, because diodes have gotten really, really cheap. So what we do actually use is a full wave bridge rectifier. Okay, this is known as a full wave bridge rectifier, where you actually have 4 diodes, and this is perhaps 361. Yes, there is a circuit for a full wave rectifier, right? So you've already seen it, isn't it? Is it? So wait, I'm confused. Yeah, I know, but so 361, you haven't done this yet? Okay, I got you. Okay, all right. So for those of you who still have to actually perform the lab, this is, well, that's the bridge rectifier circuit. And so this is basically a diamond configuration of 4 diodes, and 2 of them together handle 1 cycle each. Okay, 2 of them together handle 1 cycle each. So rather than using this diagram, let me create this one. So the way you would remember, or the way I started to remember this, is by drawing the 4 corners. And if you look at the circuit diagram, you would see that there are 2 junctions or 2 nodes where the 2 anodes meet together and the 2 cathodes come together. Okay, those are your output terminals. The place where the 2 cathodes come together is the positive output, and the place where the 2 anodes come together is the negative output. So when I draw this out, I typically just draw like 4 dots. I have 2 diodes pointing up like this, and then I have 2 diodes pointing down. Make sense? 2 pointing up, 2 pointing down. Now the place where the 2 cathodes come together is the positive output. So I'm going to put the resistor right in the middle. And then the other 2 points are where the input is coming from. So now you don't need a center tap transformer anymore. You simply take a regular transformer, connect it to the bridge rectifier circuit, and connect the load where the resistor is. So in the positive half cycle, this is what's going to happen. I'll just draw the diodes, not the entire transformer. And I have this on. And we'll have this on. Actually, rather than say this, let me say A, B, C, and D. So in the positive half cycle, diodes A and B are on, right? So A is connected to the anode over here, positive. Cathode is connected to the negative. And so both of these diodes are forward bias, hence they're on. When they're on, the current flows in this direction. And so through the load resistor, the current's again going from right to left, well, with regards to the schematic. So positive half cycle, this is what happens. You got diodes A and diodes B both on. In the negative half cycle, the polarity reverses. And when the polarity reverses, A and B turn off. Now, however, C and D turn on. So this becomes positive, this becomes negative. Now the current flows in this direction. It is still flowing from right to left. So it causes a voltage drop plus minus this way, causes a voltage drop plus minus this way. Remember, point of entry in a resistor is always positive. Point of exit is negative. So you got positive here, negative here. So in the resistor, as far as the load or as far as the load, as far as the resistor is concerned, it has continuous current flow in both half cycles. Only this time, there are two diodes instead of one that are rectifying for each cycle. All right, let's take 10 seconds, think over it. Let me know if anyone has any questions. Yes. We don't need, well, we don't need the two dual source supply. That's the advantage. Yeah, with the center tap one, we need a center tap transformer. Yeah, we need two. No, it's exactly the same. It's exactly the same. So that resistor is connected from here to here. So it's just, you know, it's ground. So this point of the resistor is connected there. I think it's just easy to visualize with this kind of diagram. Transformer. Yeah. So this is a generic, well, because it's a circuit diagram that should be applicable. So your source does not matter, right? The circuit should work with any kind of AC source, whether it's a transformer, whether it's anything else, whether it's a function generator. Now in the labs, it used to be that we used to use like I used to teach this class, different universities, electronics class for E majors, where we actually had transformers. So real life heavy duty transformers that would have like multiple outputs, and we would use those for like, you know, direct rectifier circuits. And well, as you can imagine, if open transformer with voltage coming out, it's not that safe. So you'd have to be very, very careful. Most of those transformers were like, you know, less than 20 volts, so nothing really happens. Just as a favorite point, I mean, I would point it out to students by like turning on the transformer and just standing there with holding the output, just proving to the students that, you know, nothing's going to happen to them. But anyway, in the lab classes, we just use a function generator. So the source could be anything. Could be a function generator, could be a transformer, could be anything else. Doesn't really matter. That's, huh? No, no. The only thing that happens is like somebody would make a wrong, incorrect connection, and spark would happen, and the wire would just burn out. So we'd have to like just keep replacing them every once in a while, but no accidents. Let's see. Does the operation make sense? Right? Positive half cycle, A and B are on. Negative half cycle, C and D are on. The current through the resistor still flows in the exact same direction. So the resistor still sees a output voltage that looks like this, right? A and B, and here it's C and D. So again, a full wave rectification, but now requires 4 diodes. But the advantage is that diodes are much, much cheaper than anything else. Yes. Here, it's just the same thing. It's just drawing the schematic that way. That's all, yeah. So anytime in a circuit, most circuits will have hundreds and thousands of components. So to mark the same spot in a circuit, they will have the same symbol. Meaning if there's point B in a circuit, and there are multiple components connected to point B, but in the circuit schematic, there might be like 3, 4 different components all spread far away. So in a schematic, we might just mark everything as this is point B, point B, point B, point B. So if you're reading a schematic, you would take it to mean that all of those are connected together. So in the same sense, if it shows you ground here and ground here, it means these points are connected together. This is especially true of ground, right? There will be multiple points in a circuit that are all connected to ground. And so if it's far apart in the schematic, they just draw it separately. And the reason I draw it this way is because it makes it easier to explain how it is. Okay, so the critical difference, full wave and half wave, the average value of the DC waveform is now much higher, right? Imagine if these were like mounds of dirt and you just flatten everything out. So if you flatten everything out in a half wave rectifier, you have that empty spot in the middle. Every half cycle is an empty spot, right? So whichever half cycle the rectification is taking place kind of has to fill that up. So the output voltage is 0.318. For a full wave, it's 0.617 or 0.67. Let's see, where's the diagram? Right there, 0.637. Right, so the average value of a full wave rectifier is 0.637. Sorry? Yeah. So average value is 0.637 times VM. So as an example, if your VM is 10 volts with a full wave rectifier, your DC voltage can be 6.37. Whereas with the half wave, it was only 3.18, right? Half. That's for ideal. So in a ideal, in a actual bridge rectifier circuit, we'd have 2 diode voltage drops because you need 0.7 plus 0.7 volts to actually turn on those diodes. So practical circuit requires 2 forward bias drops. .4 volts. So when you actually have a circuit like transformer, depending on what voltage we need at the output, we have to add 1.4 to that number. And there are other considerations also. This again is only taking like one or two variables into account. The first, we look at ideal conditions where we don't take into account any variables. Then we add in one variable, which is the diode turn on voltage, right? Diode turn on voltage. And the other variables are basically, well, one important factor is that it's still not a flat line, is it? It's still going all the way to 0. So it's still not a flat DC line. But before we move on to that, any questions? Yeah. Yes, absolutely. So it'll be somewhere around 5 volts or less. 5 volts or less. Now, the other consideration is that we would have filtering circuits as well as voltage regulation circuits, and that would require that you have the voltage slightly above that voltage regulator and filtering circuits. So filtering circuits is basically this. We add a capacitor to the output of a rectifier circuit. And if you took my 201 class last quarter, yeah, someone did ask me about applications for a capacitor in real life circuits, and this was an example I pointed out. I should have asked how many of you remember it. Can go back to the videos and watch it. Anyway, so the output of the rectifier circuit is still not a pure flat DC line, right? So what we do is we use the charging and discharging capabilities of a capacitor, basically the energy storage capability of a capacitor to actually smooth out the output ripple, or sorry, the output voltage. So essentially what we're doing is, if this is the load resistor in the rectifier circuit, we simply connect a capacitor in parallel across it. That's it. We connect a capacitor in parallel across it. Actually, even before the load resistor comes into the picture, the capacitor is already present in the circuit. So what happens? The output is like this, right? The output is like this. And then, of course, the empty gap in the middle. So whenever the diode is on, it conducts current, right? It conducts current, capacitor charges. So I'm drawing in red the point where the capacitor charges, okay? And then in the negative half cycle, so when diode is on, capacitor charges. When diode is off, what happens? Capacitor is now going to discharge. Remember first order transient circuits, chapter 4 from E201, charging, discharging, right? What controls or what describes the speed of charge and discharge? And time constant is R times C, right? R times C. So, and the speed of charging and discharging does not change, remains the same. So if you're charging a capacitor, it still is product of R and C. When it's discharging, it's still a product of R and C. So when you think about that, if you have a large enough value of C, what happens? It's going to take a long time to discharge. So if it takes a long time to discharge, when there is no output, when the diode is off, the capacitor is only connected to the resistor, the load resistor. So the capacitor starts discharging its internal energy through that resistor. And that is being shown by this line right here. So the capacitor is slowly discharging. And remember, if you remember first order circuit, the end result of a discharge cycle, what is the end value of a discharge? 0. So at some point in the future, that capacitor should discharge to 0. However, before it can discharge completely to 0, the next cycle hits, the positive cycle, and it starts charging again. And so what you would get is a waveform that looks like this. You get a waveform that looks like this, the one that I'm drawing out in the red. And it starts discharging again. So the waveform in red, if I was to draw it just like this on here, I would get something like this. Charge, discharge, and charge, discharge, and so on and so forth. And now, it's still not quite flat, but compared to the rest of the value of the waveform, it is very, very small and flat. So this is a much better approximation of a DC waveform with a small amount of AC thrown in it. Okay, that small amount of AC is known as a ripple. It's a small amount of AC voltage in that output. Okay, small amount of AC. Does that make sense? Right? So the takeaway point is the larger the capacitor, the flatter the output. So depending on, of course, the circuit considerations, your budget, I mean, capacitors are cheap. They're not expensive anyway. I mean, the kit I passed out, the entire kit comes from an Arduino kit, which costs like 30 bucks. And it's an Arduino microcontroller and like tons of sensors in it and all of these components in there. So all put together, the kit I passed out is probably like 10 bucks or so. So it's not that expensive. Anyway, the point I was making was the larger the capacitor, the longer the time constant, and the longer the discharge time, and the flatter your output waveform, and the smaller the ripple. Yes, you had a question?
Yeah. So, I mean, in order for that to happen, does it have to have a capacitor, like absolute charge? So does the capacitor like
it will reach full charge, yes. It won't reach full charge right at the beginning, but think about it because sorry, not think about it. If we think about it, it's 60 hertz. So 60 cycles in 1 second. So as soon as we plug in, it might not reach full charge in the first cycle, but as soon as few cycles go by, it's going to reach full charge. Does that make sense? Yeah. So just because the frequency of the waveform is, is high basically. Well, it depends on what the load is. So RC, right? RC. So if the capacitor is, let's say, 10,000 microfarads, that's the typical value you would find in any sort of like, like wall adapters. It's around 10,000 microfarads. So it's about 10 millifarads, so to speak. So it's about this big. The biggest capacitor in the kit that I passed out is only like 10 microfarads. So 10,000 microfarads, and you combine it with, let's say, a load resistance of 1 kilo ohm. So that's about, what's it, 10 millifarads times 1 kilo ohm. About 10 seconds. That's still a lot. 1 kilo ohm is not typically, what we would, yeah. It's 1,000 ohms is still a lot, yeah. But that's enough to give a nice flat output. Now, there's still a ripple in there, but it's still not quite flat DC. Now, the reason the chargers and everything are expensive is because there's a lot of components that go in there. There's voltage regulation, there's over voltage protection, over circuit protection. There's lots of things that go in there. But the typical cheap ones that we used to plug in the wall, this is what's in there, right? So this ripple voltage and the capacitor can be related with the equation C is equal to IL over VR times T. Okay, so there's a derivation behind this. It's in the book, just a couple of steps. But again, the important thing is the equation is simply current over the voltage. Okay, IL over VR, the ripple, times the time period T of the waveform. So IL is the average load current that is present in, well, that's being supplied to the load. Okay. Now you have to remember, in a half wave rectifier, you only have one half cycle. In a full wave rectifier, you have two full cycles, right? You have two full rectified cycles. And so full wave rectifier, it's IL over 2 VR times the time period T. And so depending on what kind of ripple we want, how much tolerance we have, and how much load current we want, these are just two of the variables that we can take into account while we're designing a circuit like this. Okay. So as I said, like typical adapters that I have seen, they have, 10,000 microfarads simply connected at the output. If I find one of the old adapters, I'll open it up and I'll bring it to class. I have the transformer I have, but I'm saving it for a project, so I don't want to open it up yet. Now, this, as I said, was a ripple. The capacitor we connect at the output to smooth out the waveform, and hence it is known as a smoothing capacitor. So just a smoothing capacitor. So we have the ripple, and then we have the smoothing capacitor. Yes.
When you say that VR is the peak ripple, you mean from the difference between the path and like where the arrow meets the...
Just right here. Oh.
That's it. Right.
Just this distance. Peak to peak value. Because the rest of it is just considered to be DC. And the actual average value of the waveform will be from here, from 0 all the way to the middle of that ripple. Well, approximately the middle. Does all of this make sense? Any questions? Now, when you perform this experiment in the lab, and I particularly like the way this lab has been written for 361. So what you'll do is actually you will take 2 channels of the oscilloscope and you will connect it across each half cycle. So you can see the positive half cycle being rectified, and you'll also see the negative half cycle being rectified. And then you'll use a math function, channel 1 minus channel 2, and you'll see it inverted and come out. In E major, so the E major classes, we have a lab 346. They actually don't do this procedure. So I particularly like, the way it's written up for 361. It just makes it's a little bit cooler to actually see it in person. I mean, see it on the screen. Okay, so filtered output, right? We have the bridge rectifier circuit. We have well, this is just a current limiting resistor. So 170 ohm is just a current limiting resistor. So don't worry about its function is only to limit the current, sort of to protect the circuit. And then you have a 470 microfarad filter capacitor in there, right? Again, value does not matter. Value does not matter, but it's a filtering capacitor. Then you have the output, but that output is still not quite the voltage that we need. Again, there's a small ripple still in there. And just by putting a capacitor in there is not always easier feasible. Sometimes there might be a spike in the voltage coming out. And so we want a device in there that will actually stop or prevent that spike from occurring. And that leads me into, let's see, I have about 5 minutes. So let's introduce the topic of voltage regulators. And voltage regulators basically, yes. Voltage spike is just how it's generated and transmitted. Yeah. Especially when then the power goes out and it's turned on first, then there's a rush of electrons that come in. It causes a spike, and that's why we have what do we have? What do we call those? Yes, surge protectors. Surge protectors. And we will see a real life application. The surge protectors is basically a diode circuit. Anyway, so regulator is basically, as the name suggests, it regulates the output voltage. Okay, it keeps it at a constant level. And so the topic that we're talking about is basically the Zener diode. Zener diode is a diode that is specifically configured to operate in the reverse bias region. Okay, it is specifically configured to operate in the reverse bias region. Okay. Symbol is similar to a regular diode, except the cathode terminal has whiskers at the end that look like a Z. Okay, it looks like a Z. Zener diode. It can be modeled in the forward characteristic. The Zener diode functions as a normal diode, right? It is still a regular diode. So it functions as a regular diode. This V gamma is the voltage that is required to turn the diode on. The threshold voltage, basically. Threshold voltage. Anyway, in the forward mode, the Zener diode works like a regular diode, but it's in the reverse bias mode. That's where it really shines, because that's where it's designed to operate. And when I say designed to operate, it's basically just a safe limit of operating it in reverse bias. So if you remember, in the reverse bias, what happens? Third quadrant diode characteristic is very low saturation current, right? Until basically it reaches a breakdown voltage and there's a rush of carriers, and then this remains almost perfectly straight line. And this is V and this is I, right? So it holds the voltage constant across it. So once it reaches that voltage, maximum amount of current flows through, meaning it behaves like a short circuit. It behaves like a short circuit, and it holds the voltage constant at that point. And this voltage is known as the reverse breakdown voltage. It's also known as the Zener voltage. So if a diode is designed to work or operate safely in that region, we call it the reverse. So we call it the Zener voltage. So Zener diode is specifically designed to work in that region. In the forward bias, it operates like a normal diode. But in the reverse bias, it is going to hold that voltage constant. So a Zener diode, the way it would work is it would be designed for a spec, and that spec is basically VZ, the voltage, the breakdown voltage of that Zener, and then PZ, the maximum power that the Zener diode can dissipate. Right? You cannot crank up the current indefinitely. It'll still hold the voltage constant, but if if VZ times IZ exceeds PZ, you're going to see smoke coming out. Right? So when you look at the spec sheet of the Zener diode, the first thing you should also always pay attention to is the PZ, meaning what kind of current you can limit that's going through there. All right. And just as a quick example here, so we had actually here. So we have the output at this point is basically a ripple, kind of like this, right? Now, if this level, at this level, let's say this is, I don't know, 15 volts. And my Zener diode is rated as, let's say, like 8 volts. So if I give this to a Zener diode that is rated for 8 volts, the output is going to be something like this, a flat line of 8 volts. Because Zener diode in the reverse bias is not going to conduct anything at all. The diode will stay off. It's a reverse bias. So if it's positive here, negative here, diode's going to stay off. Nothing's going to work. Once that output goes above 8 volts, the Zener diode turns on, meaning it's already operating in the breakdown region. Now the output across it remains constant at 8. So it doesn't matter how high this goes. This could go high 15 volts, 20 volts, 25 volts. As long as it doesn't provide energy that exceeds PZ, that Zener diode will continue to work without any problem. So I think this is, I don't know if this is included in lab, in the diode lab. Is this included in the diode lab, Zener diodes? Anyone?
We didn't do it, but I think it is, but
Okay.
like different in the upgrade version.
Okay. 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 All right. We'll end class here today. I'm already a couple of minutes over time. Apologize for that. Yes, quiz on, I'll post a homework quiz on Tuesday. Monday is a holiday. I will see you on Tuesday and Wednesday. All right. I'll be available all weekend long over Zoom. If you have a question, feel free to reach out to me. All right. Probably Monday night. Not right now. I'm gonna go ahead and do it. Yeah. Let me stop the meeting and then I'll be happy to. Actually, let's go outside.